Well, howdy, folks. This is odd for me too, but I'm going to try to deliver my lectures here from the living room. Um, in the next week or so, I'm going to try to set up a live stream. I don't know if this is going to be successful or not, that we could have question and answers on the fly. But in the meantime, if you have any questions or you need clarification about something that you see on these lectures, or if you have a question on a homework problem, please just send me a quick text and I'll get right back to you. And we'll keep this thing rolling along as best as we can. Well, anyway, this last half of chapter 18 that we need to look at on solubility equilibria starts with section 18.5. And essentially, the last half looks at the equilibria of marginally soluble or nearly insoluble ionic compounds when you throw them in water. For instance, if we were to take a beaker of water, and just from an environmental standpoint, let me point out that for the longest time, and I think I mentioned this in the audio lecture online, for the longest time, we didn't consider a lot of lead compounds and mercury compounds to be soluble enough in water to be of any real interest. If you threw lead chloride or mercurous chloride into water, it just sunk to the bottom of the beaker. But as our detection limits got better and better, we found that no, some of that mercury actually does dissolve in the water, and so does the lead. And even in those low concentrations pose a significant health risk. So the analysis of these marginally soluble, or what we had considered to be insoluble compounds in water, became kind of important as we found the health effects of a lot of these different heavy metals in our natural waterways. So the equilibria that's established, for instance, if we were to take something like silver chloride, a compound notoriously insoluble in water, and just threw it into a beaker of water, well, it would all just flutter down to the bottom, and you'd end up with a big pile of just silver chloride sitting down here at the bottom. It turns out that, however, a little bit of silver chloride will dissolve. The water can accommodate just the smallest amount. About 2 milligrams per liter of water is all that will actually go out into the solution. Now, it's a dynamic equilibrium. It doesn't mean that that 2 milligrams sneaks out there and it just stays there. Sometimes the silver chloride ions that actually dissolve out here will get back together and reprecipitate on one side of the pile, but that creates some room out into the solution, and another pair will dissolve on the other side. So again, a dynamic equilibrium that keeps a saturation level of silver and chloride ions out there that, again, like I mentioned, is only about 2 milligrams per liter. Well, writing an equilibrium expression for something like this, where there are reactants and products in a dynamic equilibrium with each other, is what we've been doing the last 2 chapters. We'll just take silver chloride as a solid, write an equilibrium expression with its ions that are out in solution, aqueous silver, aqueous chloride. And if we wrote an equilibrium expression for this, remember, we're kind of we don't put solids or pure liquids in our equilibrium expression, so suddenly there's no denominator in our equilibrium expression. It turns out that this equilibrium would be just the silver ions raised to the first power. Again, we would still use whatever coefficient is here as a power in our equilibrium expression. It'd be the silver raised to the first power, chloride raised to the first power, and notably absent would be the denominator, the silver chloride as a solid. Again, solids don't appear in our equilibrium expression. It wouldn't matter how big a pile was down here. The equilibrium that's established is with the water and its ability to hold just a limited number of those ions. All right, so we refer to this K. Now, in the past, we've used a Ka for weak acids, a Kb for weak bases. This is called a solubility product constant. So consequently, they use the symbol Qsp to stand for this. So you can see that writing equilibrium expressions, which is kind of how we started you off when we first introduced equilibrium, for the solids is very easy. As a matter of fact, let's do 2 or 3 other examples of just writing the equilibrium expression. Okay, here's another compound, lead arsenate. Doesn't dissolve in water to any great extent. And it's got a very, very small equilibrium constant, a small Qsp, which would imply that very few ions actually can sneak out onto the dance floor. So the solid lead arsenate would set up an equilibrium with its ions in such a way that, if this were a solid, there'd be 3 lead ions released for each one of these formula units that dissolve. So we'd have 3 leads and 2 arsenate ions, both aqueous now. Well, again, writing the equilibrium expression for this is no big deal. We just leave the solid out. The equilibrium expression would be the concentration of the lead. But remember, we have to cube it because of the 3 coefficient and the concentration of the arsenate squared. Now that's the Qsp expression then for lead arsenate. Again, nothing really to it. You just leave the solid out of the denominator. Now remember that when the lead and the arsenate show up here, the Qsp basically says how much the dance floor is willing to hold. The concentration of the lead cubed and the concentration of the arsenic squared cannot exceed what the Qsp would allow. So the Qsp pretty much dictates then how much the dance floor is willing to hold of that compound. The smaller the value for the Qsp, the less soluble that compound is. All right, let's look at one more. Okay, I lied. We're going to look at 2 more. Iron hydroxide, iron 3 hydroxide. It turns out that metal hydroxides usually are not soluble in water unless they're one of the group 1 hydroxides, the notoriously strong bases. Most other metal hydroxides are pretty insoluble in water. So it turns out that iron hydroxide as a solid, sure enough, will establish an equilibrium and release a few of the iron plus 3 ions and 3 of the hydroxides for each formula unit out into the solution. So again, the Qsp expression for this would simply be the iron concentration raised to the first power and the hydroxide cubed. Now you can understand how in some of the homework problems they're going to tie the Qsp problem to the pOH of the solution. They're not going to let that go. So there's going to be some acid-base wrinkles in some of these Qsp problems. So go back and kind of review your pH and pOH idea. All right, one more to do before we go on to the next problem. And the reason I point this out is the book is really kind of assuming that you still remember your polyatomic ions and their charges. So if that's foggy, maybe go back and review that a little bit. For instance, barium sulfate. It turns out there's quite a few sulfates that are insoluble in water, and so they use them as examples in these Qsp problems quite a bit. But barium sulfate as a solid splits up into a barium ion. And they'll assume that you know that you recognize that as a sulfate ion, that it doesn't split up into its individual elements, but it's a polyatomic ion that's pretty common. And again, there's only one of each, of one barium, one sulfate. So the Qsp for this, very easy, is just simply the barium concentration times the sulfate concentration. All right, so there's 3 or 4 examples of how to write equilibrium expressions. As a matter of fact, the problems that are in your text for this are the ones that are covered in section 18.5. And so, again, take a look at the homework problems. Pause this every now and then, and maybe look at those just to see how they correlate with what we're talking about here. All right, well, the way we've done equilibrium problems in the past, just going to continue. We either give you a way to figure out these molarities so that you can calculate for us what the Qsp is for a compound, or we give you the Qsp and then ask you to tell us what are the molarities of those ions that are in the solution. What's the solubility? All right, well, let's look at both of those. Okay, well, first let's look at calculating the Qsp of a compound given its solubility. Now I should point out that the book sometimes gives the solubility of a compound in grams per liter, but in our equilibrium expression that won't work. It has to be in moles per liter. So the conversion from grams to liter to moles per liter requires that you divide by the molecular weight of the compound. All right, for example, silver chloride, one that we were just discussing a little bit ago. I mentioned it has a solubility of around 2 milligrams per liter. So silver chloride, its solubility is listed as 1.9 times 10 to the minus 3 grams per liter. Let's see if we can use that information then to find the Qsp. Well, again, the first thing we have to do is convert this grams per liter into moles per liter. So let me make a little bit of room up here on top and we'll do that calculation real quick. Okay, so silver chloride weighs 143.4 grams per mole. That's if we sum up the atomic masses of the two elements that's there. So 1.9 times 10 to the minus third grams per liter. If we were to say, well, 1 mole of this weighs 143.4, so essentially we're dividing by the molecular weight, that would replace the grams with moles of silver chloride. This turns out to be 1.3 times 10 to the minus 5 moles per liter of silver chloride. Now the thing to remember is that when that many moles per liter of silver chloride dissolves, it's going to create 1.3 times 10 to the minus 5th moles per liter of silver and 1.3 times 10 to the minus 5th moles per liter of chloride ion. So if we're trying to calculate the Qsp for this is going to be the concentration of the silver and the concentration of the chloride. So in essence, we'd take the 1.3 times 10 to the minus 5th for each of those. Which comes out to be 1.7 times 10 to the minus 10th. Again, a very small number for the Qsp, but we kind of anticipated that since silver chloride is not very soluble in water and would have a very, very small Qsp. Okay, well, let's do another example of this, but let's take it up a notch. Okay, well, the book usually takes it pretty easy on you. Instead of giving you grams per liter and making you divide by the molecular weight to change things to molarities, they'll generally just give it to you in moles per liter. And that way you can just plug it right into the equilibrium expression. For example, here's one from the textbook. They said lead arsenate. This is one that we wrote the equilibrium expression for just a second ago. This lead Roman numeral 2 arsenate has a solubility of 3.34 times 10 to the minus 8th moles per liter. Now that's moles of lead arsenate per liter. So keep in mind that that is going to make 3 times as much lead ion in the solution. Again, because if it's this many moles of lead arsenate and there's 3 leads in each one, that number times 3 would represent the concentration of the lead. And there's 2 arsenates in each one. So I'd have to take this times 2 to get the concentration of the arsenate. But here's what's interesting about this. Not only did I have to multiply them by these factors because of how many are in the formula, but when I calculate the Qsp, I'm going to have to cube this also because of the mass action requirement for equilibrium. And I'm going to have to square the arsenate. So not only does this number get tripled, it also gets cubed. This one's going to get doubled for the arsenate and also squared. Well, let's go ahead and put the numbers in and see what this comes out. All right, well, the Qsp would equal 3 times the 3.34 10 to the minus 8th, this is for the lead, cubed, times 2 times the 3.34, 10 to the minus 8, squared for the arsenate. Well, it turns out the final answer here is very, very small. It comes out to be 4.5 times 10 to the minus 36th power. That's a mighty small Qsp. So again, this compound is really not soluble in water. All right, so you can understand then that this is the way they'll first approach this. I think section 18.5 and 18.6 talk about the fact that if we give you the solubility of the compound, surely you can figure out then what their molarities are of each of the ions. And knowing that you'd raise them to their coefficient in the equilibrium expression, you can calculate the Qsp for a compound. So there's not a whole lot of spin that they can put on these. You'll find a couple of these in the pre-lab for the lab that I'm going to send you for Wednesday. And again, you'll find several of these on the audio lecture that you'll find on the website. So hopefully this will help supplement what you found on the website and what we're going to do in lab this week. All right, well, let's take another approach to this. I mentioned that we like to do these forward and backward, and so rather than give you the molarities, what if we gave you the Qsp and then asked you to calculate for us, well, what's the solubility of the compound? All right, let's take a look at those. Okay, well, we approached the Qsps from one direction. Let's approach it from the other direction. This time we're going to look at calculating the solubility of a compound from the Qsp. And the first one I want to do is calcium sulfate. Nice, easy one. It's just got two ions, a calcium and a sulfate. The Qsp for it is 2.4 10 to the minus 5. That's actually not that very small. I'd say several hundred milligrams of this will probably dissolve in a liter of water, but still marginally soluble. And so let's calculate its solubility first in moles per liter, which will come directly from the equilibrium expression, and then let's do it in grams per liter. Okay, well, the calcium sulfate is going to set up an equilibrium with calcium ions, aqueous, and sulfate ions, aqueous. Now, even though this doesn't appear in the equilibrium expression, for every X amount of it that actually creeps out onto the dance floor, we would get an X number of calciums and an X number of sulfates. They would end up being equal. And since the Qsp expression for calcium sulfate is simply the calcium raised to the first power, and the sulfate likewise raised to the first power, we could essentially just plug in our variables now, and since we know the Qsp for this compound was 2.4 times 10 to the minus 5th, that was given, this is going to be equal to X times X. Well, that's pretty easy. Just take a quick square root, and we find out that X is 4.9 times 10 to the minus 3. Now, since these are molarities, there's our first answer. This is how many moles of calcium sulfate will dissolve per liter. Because again, for that X amount that dissolves, we get an X amount of calciums and an X amount of sulfates. Okay, so pretty easy. Well, I asked, well, could we give that in grams per liter? Well, it turns out that calcium sulfate weighs 136.2 grams per mole. So really just a quick product of this moles per liter of calcium sulfate times the 136.2. As a matter of fact, let me just do this up above. If we took 4.9, 10 to the minus 3 moles per liter times the 136.2 grams per mole, we end up with 0.67 grams per liter. Can you see that on the screen? 0.67. So again, I mentioned that, with a Qsp that's relatively large like that, 10 to the minus 5th is not that small. A little bit, half a gram, a little more than half a gram of calcium sulfate will dissolve in a liter of water. Okay, so you can see that this wasn't very tough. We've done tougher equilibrium solutions than this when we were looking at the weak acids. And there's no chance of a quadratic appearing here because, again, there's no denominator in our equilibrium expression to have any subtracted x's from that lead to that quadratic. All right, well, let's take this up a notch and look at one more. Let's put something with more ions out on the floor. Okay, hopefully I didn't write that up there too high. The Qsp for this magnesium arsenate is 2 times 10 to the minus 20th power. And so in this problem, again, let's calculate its solubility in moles per liter and then grams per liter. All right, now in this case, and let me erase a couple of things here. Now that we've established what it is we're going to do, I need to set up our variables, our ICE table. All right, so for every X amount of the arsenate, the magnesium arsenate that dissolves, we would end up with a 3X amount of the magnesium and a 2X amount of the arsenate ion. Now here's where this gets interesting. This is probably the worst case scenario with this many ions out on the floor. But the Qsp for this is the concentration of the magnesium cubed and the concentration of the arsenate squared. Well, if we plug in what we know, 2 times 10 to the minus 20th for our Qsp, this is 3x cubed. Again, we had a triplet because there's 3 magnesiums in each formula unit, but we had to cube it because of the equilibrium expression. And we'd have 2x for the arsenate squared. Well, if you expand that, 3 cubed is 27, 2 squared is 4. That's 108 x to the 5th power. And we need to solve for x. All right, well, let me make a little bit of room then. Okay, this means then that our x value is going to be the 5th root of 2 times 10 to the minus 20th over 108. So again, find your y to the x key on your calculator and figure out how to do your 5th roots. There's always the logarithm way to do it, but again, figure out how to do a 5th root. You're going to find that this comes out to be 4.5 times 10 to the minus 5th moles per liter of the magnesium arsenate. I don't have room there to write the formula. But that's the number of moles per liter of that compound that would dissolve. Now, I asked you to also go as far as to find it in grams per liter. To get that, all we need to do is multiply that times the molecular weight. Well, the molecular weight for magnesium arsenate is 350.7 grams per mole. That's if you sum up everything that's in its formula. So multiplying this times 350, what did I say, 350.7 grams per mole, we end up with 1.6 times 10 to the minus 2 grams per liter. So we're talking 16 milligrams of this stuff will dissolve in a liter of water. But again, it had a pretty small Qsp. But you can understand that given the number of ions, it made the arithmetic at least a little bit more complex, that we had to do a 5th root. So again, with more ions, your variables get a little bit more complicated, but the math isn't insurmountable. So if you have any questions on this, on how to set these up, again, just text me or email me, and I'll do some more examples and shoot them your way. But I think you'll find on the website there's a lot of good stuff. If you listen to the audio lecture and go through the problem sets that I've got on the website and the tutorial quizzes, you'll find that there's plenty of material for you to practice on to get these problems. All right, well, let's look now at something that we introduced back in our acid-base chapter, and that was something called the common ion effect. For instance, what if we tried to dissolve that magnesium arsenate in a solution that already had a magnesium compound dissolved in it? meaning the dance floor was already full of magnesiums. Well, if that ion is in common with your equilibrium, we have to count it. And it might inhibit the magnesium arsenate from getting out on the dance floor if it sees a dance floor already littered with magnesium ions. All right, well, let me clear the blackboard and we'll try one of these common ion problems. All right, well, again, here's your typical common ion type problem. If we were to look at the solubility of a compound like barium fluoride, it's got a reasonably small Qsp, 1 times 10 to the minus 6th, and looked to see, well, how much of it would dissolve just in pure water? That's what we've been looking at so far, is just determining solubility based on the Qsp. But what if we tried to dissolve the same barium fluoride in a solution that was 0.15 molar in sodium fluoride? Meaning it wasn't just an empty dance floor, just all water. There was already a lot of fluoride ions out there. Well, I think you'll see that the barium fluoride has a hard time forcing its way out onto the dance floor when it's already that packed with one of its ions. So let's do the one in pure water first. Okay, so the barium fluoride as a solid will establish an equilibrium to give up a barium ion and 2 fluoride ions, aqueous. All right, so the bariums would be X and the fluorides would be 2X for each X amount of barium fluoride that got across the arrow. Well, the Qsp for this again is 1 times 10 to the minus 6th and would be equal to the barium concentration times the fluoride concentration squared. So plugging in what we know, we were given the Qsp of 1 times 10 to the minus 6th. That's going to be equal to X times 2X squared. Again, remember, we had to double this because there's 2 fluorides in each formula, but also we had to square it because of the equilibrium expression. So this ends up being 4x cubed. So in that case, x is going to be equal to the cube root of 1 times 10 to the minus 6th over 4, which turns out to be, let me fast forward because I didn't calculate this. Hold on just a second. Actually, Devin, get busy on this. Let's see, 1 times 10 to the minus 6th. I can't even work my calculator. 1 to the minus 6th. All right, we got to divide it by 4. And then we got to take the cube root of that. Let me do that here real quick. I got 6.3 times 10 to the minus 3. Now, again, that X represents the moles per liter of barium fluoride that would actually dissolve. So let's put that down here. This is moles per liter of the barium fluoride. Okay, so you can see in pure water then, 6.3 times 10 to the minus 3 moles per liter is pretty small. We could go on to ask for that solubility in grams per liter. Again, we'd multiply by the molecular weight of the barium fluoride. But for this purpose, let's just leave it in moles per liter. All right, well now what I'd like to do is show how this tries to dissolve in a solution that's already got a bunch of fluoride ions in the solution. So again, remember this number, 6.3, 10 to the minus 3 moles per liter. Okay, so we're going to look at the same equilibrium, but this time the fluoride doesn't start off with 0. Normally in our ice table, remember, we'd start off with 0 and 0, and then we'd add an x and add a 2x in order to get our equilibrium amount. I kind of cut straight to the chase and just looked at x and 2x. But in this case, we're not starting with 0 of the fluoride. We're starting with 0.15 molar. Well, in this case, then, the equilibrium amount is still going to be x for the barium, but here it's going to be 0.15 plus 2x for the fluoride. Because, again, we had 0.15 of the fluoride ion out there already from the 0.15 molar sodium fluoride that we said we were going to try to dissolve it in. Remember, the sodium is just a spectator ion. The fluoride is the one that's in common with this equilibrium. All right, well, if that's the case, let's just go ahead and plug this in then. to our Qsp expression. Remember, the Qsp was 1 times 10 to the minus 6th. This is going to be the barium concentration raised to the first power and the fluoride concentration squared. Now, here's an issue that we had when we did the weak acids. A lot of times when we added X's onto a big mountainous pile of ions that were already there, the X's became insignificant. Now, if you remember, the X, when we just calculated it a moment ago, came out 6.3 10 to the minus 3. That's 0.006. So that's really even beyond the significant figures here for 0.15. This 0.15 is so much larger than the X value. And remember, the X is even going to be smaller this time, that we can say, well, those two X's are actually insignificant compared to this huge pile of fluoride that we've got there. So this is actually approximately equal to X times just 0.15 squared, meaning the 2X that's added to the 0.15 becomes insignificant. Well, now that makes this much easier to solve. I don't even have to do a square root. All I have to do is simply divide both sides by the 0.15 squared, and I've got my value for X. So let me erase a little bit and we'll calculate that. All right, so in this case, X is going to be equal to 1.0 10 to the minus 6th divided by the 0.15 squared. Let me calculate that real quick. Somebody back me up out there. 10 to the minus 6th divided by the 0.15 squared. I got 4.44 10 to the minus 5th. Actually, we're only good to a couple sig figs. 4.4 times 10 to the minus 5th. I make that look like a 5 moles per liter. Now, think about this. When we dissolved the barium fluoride in pure water, this came out 6.3 10 to the minus 3rd. That's almost 100 times, that's more than 100 times bigger. More solubility when it was in pure water. When we tried to dissolve it out onto a floor where there was this mountainous pile of fluorides, that affected the equilibrium and consequently pushed it back toward the solid. So much less of the barium fluoride will dissolve, like I said, if there were barium ions out there or fluoride ions. In this case, it was the fluoride ions. All right, well, let's try one more. And this one's a metal hydroxide. I mentioned before that metal hydroxides aren't very soluble in water. Nickel hydroxide is one of them. A little bit of nickel, a little bit of hydroxide might creep out onto the dance floor, but the Qsp is 2 times 10 to the minus 15th. So it turns out that if we let the amount of nickel that creeps out here equal X and the amount of hydroxide 2X just in pure water, then this 2 times 10 to the minus 15th ends up equaling X times 2X squared. Again, we're faced with one of those 4X cubed problems. And the X value turns out to be the cube root then of 2 times 10 to the minus 15th over 4. Well, that value turns out to be 7.9 times 10 to the minus 6th. And that's in moles per liter. So again, pretty small. Only 8 millionths of a mole can actually dissolve per liter. But what if we try to dissolve this nickel hydroxide into water? And again, let me point out, if they wanted that in grams per liter, we'd have to multiply by the molecular weight of nickel hydroxide. And Tro is notorious for asking for that at the end of the homework problems, and so am I. So again, be aware of how we're asking you to form your answer, whether in moles per liter or grams per liter. Now, if we want to look at the same solubility, though, suppose we try to dissolve the nickel hydroxide in a solution that had a really high pH, meaning there were a whole bunch of hydroxides already in there floating around. As a matter of fact, let's push the pH up to like 12 and see how much it's going to inhibit that solubility of 7.9 times 10 to the minus 6th. All right, well, let me erase this and we'll make a little room. Okay, suppose the pH is 12. Well, that means that the pOH is 2, and means that the hydroxide concentration from this is 10 to the minus 2 power, or I should say 1 times 10 to the minus 2. Well, that's a heck of a lot more than we would get from the nickel hydroxide. So in essence, we got a common ion situation here. Let's go ahead and set up an ice table. All right, so here's our hydroxide from the fact that our solution is a pOH of 2 is 1 times 10 to the minus 2. All right, well, 0 for the nickel and 0 for the hydroxide. Not this time, it's not pure water. This is 1 times 10 to the minus 2. We would pick up an X amount, pick up a 2X amount to give us a value of X for the nickel, and a value of 1 times 10 to the minus 2 plus 2X for the hydroxide. But again, this is one of those situations where that X was 10 to the minus 6th power, so much smaller than what's there already on the floor that it's insignificant compared to this mountainous pile of hydroxide that's there. So in essence, this is 1 times 10 to the minus 2. Well, let's go ahead and plug these variables then into our equilibrium expression. We know the Qsp for the nickel hydroxide. Let's see how much this hydroxide there inhibited the nickel hydroxide from dissolving. All right, well, the Qsp we said was 2 times 10 to the minus 15th, which remember is equal to the nickel times the hydroxide squared. So 2 times 10 to the minus 15th is going to be equal to X. Now in this case, normally we'd have the 1 times 10 to the minus 2 plus 2X, but we're going to ignore that 2X. Make it 1 times 10 to the minus 2 squared. Again, that's a mountainous pile of hydroxide in comparison. Okay, well, to calculate and solve for X, pretty easy now. The X value is going to be 2 times 10 to the minus 15th divided by 1 times 10 to the minus 2 squared. Well, this turns out to be, that would be 10 to the minus 4. If we do that, this is going to be 2 times 10 to the minus 11th moles per liter. Remember, it was around 8 times 10 to the minus 6th moles per liter, 5 orders of magnitude larger when there was no hydroxide on the dance floor. If we just released the nickel out into just empty water, we could actually get, what was that value? 7.9 times 10 to the minus 6th moles per liter. But if we try to do this in a solution that's already littered with hydroxides, that's going to affect the equilibrium. You can understand that was like Le Chatelier's principle. We added more product, it shifted it back toward the reactants, and consequently less of the solid nickel hydroxide could get out onto the floor. Significantly less. Hot diggity, isn't this fun? All right. Okay, well, the solubility of a lot of different compounds can be affected by the pH of the solution. For instance, barium fluoride, one that we used as an example earlier, does not dissolve very well in water. It had a Qsp 1 times 10 to the minus 6th. But it turns out if we throw some hydrogen ions in here, it's pretty obvious who they're going to go after. We just did a chapter on weak acids and bases, but a hydrogen ion is not going to come after the barium. The hydrogen's got a positive charge. It's going to come after the fluoride. And fluoride can be very accommodating to the hydrogen because HF is a weak acid, meaning it likes having a hydrogen attached to it. So if we were to throw a hydrogen ion in here and it removed one of the fluorides and made an HF out of it, it would no longer affect this equilibrium, and it would have created a hole there where we took that fluoride away. Well, if I continue to dump a whole bunch of H pluses in there and keep sweeping fluorides off the dance floor, Le Chatelier's principle says that if I'm removing product from this equilibrium, the equilibrium is going to shift to replace it. So sure enough, the more acid we throw in here, the more barium fluoride can actually get across the arrow and dissolve. So it turns out that, yeah, barium fluoride is much more soluble in an acidic solution than it would be in just pure water. And that would be the case every time this anion is the anion of a weak acid. Now that's a lot of anions. Remember, there's only 6 anions that wouldn't do that. Those are the anions of the strong acids. So that means pretty much any compound that has an anion over here that's not a chloride, a bromide, an iodide, a nitrate, you know, the 6, then sure enough, if you try to dissolve it in an acid, it's going to work a lot better than if you try to dissolve it in water. All right, well, let's look at another example. Okay, this compound, silver acetate, not very soluble in water. As a matter of fact, we're going to measure its Qsp this week in our Qsp lab. But it turns out that in pure water, not very soluble, but in acid, yes. Well, that's again because the hydrogen ions are going to combine with these acetates. Acetate is the anion of acetic acid. It's a weak acid. So consequently, the hydrogens will combine with it, sweeping it off the dance floor, creating a hole there. Well, that allows more silver acetate to dissolve. And sure enough, it'll dissolve pretty good in acid, but not in pure water. But here's something kind of interesting. It turns out that silver hydroxide, also being a weak base, will precipitate. So if we were to put some hydroxide in here, well, it would combine with the silver and remove the silver from the equilibrium and precipitate it out as silver hydroxide. In essence, then, the silver acetate would see that as an opening for more of it to dissolve. So this is an interesting compound. It has the cation of a weak base and the anion of a weak acid. Consequently, in pure water, it doesn't fare too well. But in acid, it dissolves pretty well because the acid removes the acetate ions from the picture. And it dissolves pretty well in a base because it removes the silver from the picture. Either one is going to create a void on the dance floor and allow more of the silver acetate to dissolve. So in general, here's the rule. Okay, so compounds are just going to be more soluble in acid than they would be in pure water if the anion of the compound is that of a weak acid. Again, putting the acid in there sweeps that anion off the floor, off the dance floor, creating a void. Suddenly more compound can dissolve. On the other hand, compounds that are more soluble in base than they are in pure water are those that have a cation from a weak base. Again, because the hydroxide seeks those out, sweeps them off the dance floor. So that pretty much sums up how pH affects the solubility of compounds. All right, well, next we need to look at the predicting of precipitations. What happens when we bring 2 ions together and throw them on the dance floor, and what happens if we exceed what the dance floor will hold, if we oversaturate the solution? Will a precipitation occur? All right, that's where we're headed. Okay, well, we're breaking into section 18.6 on predicting precipitations. And just a quick story. When I was working for the State Water Survey, and we worked on a lot of rivers in Illinois, there was one particular river, and honestly, I don't remember the name of it, but there were 2 industries that were on the waterway where one got caught dumping some lead nitrate because it was reasonably soluble, and they were flushing some tanks or something, and a whole bunch of lead nitrate ended up getting out into this waterway. Well, lead nitrate, lead Roman numeral 2 nitrate, pretty soluble, and it's colorless in solution. There's not a whole lot of tint to it, so it went unnoticed. But another industry downstream from this one was dumping some sodium chromate, which is reasonably soluble in water. And although it has kind of a slight yellowish tinge to it, the waterways in Illinois all have a slight yellowish tinge to them, so it went unnoticed. But it turned out that lead chromate is not soluble in water. It's got a very small Qsp. And suddenly, when the effluent from this factory went downstream and met the effluent from this factory, a whole bunch of lead chromate, bright orange, started to form as a solid on the surface of the water. And so this big orange plume immediately emerged from this second factory. Well, they were really only half of the pollution. The fingers immediately pointed at them, that you're dumping all this orange stuff out there. Well, they were only dumping half of it. The factory that was upstream was dumping the other half. So here's an instance where two ions that are sort of incompatible with one another met as one came downstream and met the other. So they came from different sources, but their individual molarities exceeded what the Qsp would allow for that compound. And consequently, somebody had to sit down. It shifted the equilibrium. So again, this is kind of important when you're looking at combining solutions. There might end up being an incompatible pair of ions out on the dance floor, and suddenly a precipitate occurs. All right, well, let's look at a situation like that with a compound that we've just done a problem with, calcium sulfate. Hold on just a second. Okay, so predicting precipitation. We need to go back and look at something. We looked back in our equilibrium chapter. We looked at what was called a Q sub C. That was called the reaction quotient. And it said, well, what if we look at the current conditions of an equilibrium? Say it's not at equilibrium, it's either south of it or north of it. If we plug in the actual current conditions of the ions and see whether or not the Q sub C exceeded the K sub C, meaning that there was too much product to be at equilibrium, we knew the equilibrium would shift back toward the reactant side. We're going to use that same concept and use a Qsp. So in essence then, the Qsp would equal the concentrations of the ions of your compound raised to their powers, X and Y. But let's use the current value. At the instant that the two solutions met, like my story in the river, if we put those current molarities and then ask ourselves, well, does the Qsp exceed the Ksp? If so, precipitation is going to occur. Because you've got the dance floor too crowded. You've exceeded what the Ksp would allow. All right, well, let's apply this to a problem, again, one that we did earlier. Let's look at calcium sulfate. I have a sheet here. Now, suppose we've got a solution. Let's say, suppose we make a solution that has a calcium concentration equal to 0.0052 molar. Suppose we brought the calcium to the dance with some very soluble anion, like a nitrate. And then suppose we brought some sulfate ions in, and we could bring them in with a sodium that would be very soluble, and suppose we made the solution 0.0041 molar. All right, well, if we made them those two concentrations, my question is, will a precipitate of calcium sulfate happen? Say, will calcium sulfate precipitate? Now, the Ksp for calcium sulfate from our previous example was 2.4 times 10 to the minus fifth. So we just need to know, did we exceed what we're allowed by the Ksp? All right, well, here's our two molarities. Let's go ahead and set up a Qsp expression. Now, the Qsp is the same as the Ksp expression. Remember that calcium sulfate simply splits up into a calcium ion and a sulfate ion. So that means the Qsp would simply be the concentration of the calcium currently and the sulfate currently. We just want to know, is that bigger than or less than the Ksp? If it's bigger than the Qsp, then we've got the dance floor too crowded. Somebody's going to have to sit down. However, if we're less than the Qsp, that means there's still room out in the solution. No precipitate would happen. All right, well, we were given the calcium concentration of 0.0052. And, raised to the first power, the sulfate was 0.0041. So our question is, will this exceed the Qsp? Let me grab my calculator. Back me up there, Devin. Okay, 0.0052 times 0.0041. I got 2.13 10 to the minus fifth. Ever so slightly smaller than our Qsp. We have not reached the ceiling yet. So less than the Qsp, no precipitate. Simple as that. Okay, so it's much like the Q sub C problems that we did back in our Equilibrium chapter. Now this one's kind of a simple one because everybody was just raised to the first power and we just gave you the current molarities and just said, okay, did we exceed the Qsp? The more complicated form of this problem is if we bring two solutions together and they make you recalculate what the new molarities of the ions are in order to plug them into your Qsp expression. So let me get one of those ready on the board here and we'll do that one. Hold on. Okay, in this one we're going to take it up a notch. Suppose that we added 255 milliliters of a solution of lead nitrate. Concentration is 0.00016 molar. Now we're really only interested in the lead ion. Lead nitrate is completely soluble in water, so it's going to result in this concentration of the lead, at least in this 255 mils. We're going to mix that with 456 milliliters of 0.00023 molar sodium sulfate. Okay, so here's a situation where two solutions meet. But it turns out we want to know, did we overcrowd the dance floor with leads and sulfate so much so that lead sulfate would have to sit down and precipitate? We'll tell you the Qsp says, well, the dance floor is willing to hold enough to reach a Qsp of 1.7 times 10 to the minus 8th. What we need to do is figure out, well, what's our current Qsp? Now that's where the trick comes in, because we're mixing two volumes together, so the new total volume is going to be much larger. We need to refigure then what's the molarity of the lead ion after these two volumes have been added together, and what's the new molarity of the sulfate after these two volumes have been added together. Well, I'm going to need a little bit of room. Let me erase this and we'll do that calculation. Okay. So here's the number crunching part of this. We mixed 255 mils of the lead nitrate, and I'm only looking at the lead. I let the nitrate go. It was a spectator ion. And 0.0016 millimoles per milliliter. So I'm going to multiply the molarity times the number of milliliters. That gave me 0.0408 millimoles of lead ions in there. But remember, now I've mixed two volumes together. Let me go ahead and calculate the sulfates, and then we'll do both their molarities together. The sodium sulfate, we mixed 456 mils, and it was 0.00023 molar in sulfate ions. That gave us 0.105 millimoles of sulfate. Well, remember now they're in a total volume of, over here, 711 milliliters. So I'm going to divide each one. For instance, the concentration of the lead would essentially then be the 0.0408 millimoles of lead divided by the 711 milliliters. Devin, what do you got there? 0.0408 divided by 711. I got I'm going to round it to 2 sig figs, 5.7 10 to the minus fifth. Molar in lead. This is after the two were mixed together. This is how much lead would actually be floating around in there in molarity. Let's do the same thing for the sulfate. The sulfate concentration would be its number of millimoles, 0.105 millimoles of sulfate, divided by the 711 milliliters that we're in. So let's see, 0.105 divided by the 711. Turns out to be 1.5 times 10 to the minus 4 molar in sulfate. All right, so here's our two new molarities. The current molarities after those two solutions have been mixed together. Well, let me make a little bit of room and let's calculate a Qsp and let's see how it compares to the Ksp of 2.4 times 10. Oh, what was that Ksp? We had it up there on the board just a second ago. Hold on a second. Let me see if I can find it. I can't find my sheet. Oh yeah, here we go. The Ksp was 1.7 times 10 to the minus 8th. Well, let me make a little room and we'll take the product of those two numbers. All right, here we go. Our Qsp value is going to be the current concentration of the lead, which is 5.7, 10 to the minus 5th, times the current concentration of the sulfate. Remember, lead sulfate is just one of each of these, so they're both raised to the first power. This is 1.5 times 10 to the minus 4. So that our Qsp value, which we want to compare to our Ksp, comes out to be, let's see, 5.7, 10 to the minus 5th, times 1.5, 10 to the minus 4, comes out 8.55, 10 to the minus 9th. Let's say 8.6, 10 to the minus 9th. Well, remember our Ksp was 1.7 times 10 to the minus 8th. So again, here's a case where we have not exceeded the Ksp. There's still a little bit of room on the dance floor. So this is less than the Qsp of 1.7, 10 to the minus 8th. So no precipitation is going to occur. Sorry, I should have picked one where we exceeded it. There'll be plenty of those in the homework. But hopefully everybody sees the concept here. Just like before, we're looking at which way is the equilibrium shifting. Is it shifting back toward the solid, which would mean precipitation, or is it shifting back toward the ions, which would mean there's still room on the dance floor? So we're just looking, again, at a Q sub C versus K sub C. In this case, it's solubility products. All right, now that was section 18.6. And the homework problems, by the way, that you'll want to look at for this, let me get them real quick. Okay, the homework problems for the common ion effect and the equilibrium expressions were problems numbers 95, 97, and 99 in chapter 18. With the predicting precipitation, there were two of them that I assigned, number 101 and number 105. So now might be the time to just sit down after you've seen this and you've seen a few examples and try a few of those homework problems. Okay, well, hopefully this wasn't too painful a way to look at these lectures. I've still got a couple of topics left at the end of chapter 18 before we start our chapter on thermodynamics. And again, if you have any questions about any of the examples that you saw here or any of the examples that you'll see in the lab that I'm about to send you, don't hesitate. Call me, text me, email me, and we'll just keep this up. I'll deliver 2 or 3 of these a week through May, and when we get closer to that third exam, I'll give you a heads up and we'll figure out how we're actually going to do that. But anyhow, I'll see you Wednesday. Have a great day.